And I will speak about my research that was started in Switzerland and finalized in the project FOTONIKA LV. This research finalized with the moment with the paper, and I'm looking for possibility to go deeper in this research too. And I will speak shortly about this some points, some physics to understand what it is about experiment and results, and also how it can be related to astronomy. So the physics is related to magneto-optical effects. So if it is interplay of two things, coherent light that creates coherence or polarization, and magnetic field that destroys coherence. And this magneto-optical effects is so related to resonances, some kinds of resonances when larger frequency of magnetic field, precession of angular momenta of atoms, of molecules, is equal to some frequency of, for example, of modulation of light or modulation of an additional magnetic field. This type of the sample, there was a cubic cell filled with cesium in a butter gas, a camera, big astronomical big camera, and laser light was formed with optical system and expanded and slit into a sheet, narrow sheet of light, quasi two-dimensional sheet of light, the size of cell. And also there were built three configurations of magnetic fields, of inhomogeneous magnetic fields. So it's with anti-Helmholtz coils, with 8 wires coils, and with 1 coils and Helmholtz, with 1 long wire and Helmholtz coil. So it is simulated magnetic fields with vectors, magnetic field vectors, and equipotential lines, all 3 configurations. This configuration is more simple, but it's related to atom traps. You can, there is one zero field point inside, with which you can manipulate. So we have used a theory that was based on simple algebraic expressions made before by Professor Antoine Weiss and his people. It's for circularly polarized light and for linearly polarized light. And here is the results. The result was here is he result for one configuration of magnetic field, for other, and for third configuration. Above are theoretical calculations, below are experimental data. So you see it's two-dimensional Hanna effect when it is excited by the circular polarized light comes from left to right. And you see that circularly polarized light polarize atoms in a direction of light, of beam. And so when magnetic field is parallel to this polarization of atoms, so atoms become dark, and when perpendicular atoms become bright. It's a two-dimensional Hanna effect. So it's a nice way to see such a fundamental things like resonance. We went further, and we would like to know, we we would like to know what fields are there. So we put oscillating magnetic field to obtain resonance. This oscillation composed from some harmonics, some sinusoidal waves, for example 5 or equidistant. And so here we can see here in the experimental data that the places of magnetic fields where modulus of magnetic fields is equal, like in modulus magnetic lines. So by this method, for these cells, we can construct vector of magnetic fields direction, but only modulus for the moment. Other patterns we can get using linear polarization. So there is, in this case, we have even better experimental theoretical description of experimental data. So for different virtual methods. Also, we have used other kind of resonances, so-called Bloom resonance or phase resonances, when polarization of exciting light is modulated. In this case, we have equivalent transition, we have dark curtains. It's for 3 different configurations. The goals of this study, main goal, was also to reconstruct magnetic fields, unknown magnetic fields. And here, for example, there is a so-called magnetic gel with equidistant resonance lines, equimodulus lines. And here we bring close to the cell some weak magnetic object, as this Torlop set screw. And we see such a spider and so on. It's a very simple example. The goal was, further goal was in Fribourg to visualization of magnetic nanoparticles. And so the theoretical model should be improved, and of course it's interesting to reconstruct the direction of magnetic fields. Let's say why. So some years ago, some, for example, astronomers from United States, it's a Lazarian group, they proposed to, they are theoreticians, they proposed to measure magnetic field by the same techniques using ground state alignment of such objects like galaxies and so on, nebulas. And I don't know why they propose to use to reconstruct magnetic field direction by measuring polarization of spectral lines. I don't know why, because for the moment it was not realized experimentally. Also, before some years, Professor Bucher from Berkeley proposed to measure by the same technique magnetic field of S using potassium atoms in ionosphere somewhere. And also it was not realized before to this moment, to my knowledge. And the main point that I would like to say that is maybe the best point to start such studies or measurement of a remote object is to start from the top of the table. Indeed, this what I did in these studies. It was remote sensing of very close object. In principle, people find the proper proper atomic medium can develop such technique for astronomers on the top of the table. That's all.